The Milky Way rests within a small gathering of galaxies called the local group, a gravitational community spread across several million light-years of space. The group is not arranged like a neat sphere or a fixed pattern. Its members occupy a broad, uneven volume, shaped by gravity, past motion, and the gradual expansion of the universe. Between the galaxies lies almost complete darkness, interrupted only by thin traces of gas, faint radiation, and the light of distant stars. From this outer perspective, the Milky Way appears not as an isolated island, but as one large member of a quiet, cosmic neighborhood. The local group contains several dozen known galaxies, though the exact count changes as new extremely faint systems are discovered. Most are dwarf galaxies, small collections of stars held together by gravity. Some contain only a few million stars, while the largest members contain hundreds of billions. The Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy dominate the group by mass and size. Around them move many smaller companions, some in wide orbits and others on paths that bring them closer to the larger galaxies. The Milky Way and Andromeda are the two principal galaxies of the local group. Each is a large spiral galaxy with a broad disk, a central concentration of stars, and an extended outer region. They are separated by about 2.5 million light-years. Across that distance, their light travels for millions of years before reaching the other. The separation is immense on any local scale, yet small compared with the distances between large galaxy groups across the wider universe. Andromeda appears slightly larger in visible extent and may contain more stars, though measurements of total mass remain uncertain. The Milky Way may have a comparable amount of dark matter, the unseen material inferred from its gravitational effects. Observations indicate that both galaxies are embedded in massive gravitational regions extending far beyond their bright stellar disks. Their outer influence overlaps the wider structure of the local group, helping bind smaller galaxies and diffuse matter into a shared environment. The Triangulum Galaxy is the third largest spiral member. It lies farther from the Milky Way than Andromeda and contains fewer stars than either of the two dominant galaxies. Its disk shows active regions where gas forms new stars. Its motion suggests that it may be gravitationally linked with Andromeda, though the exact history of their interaction remains under study. Together, these three spiral galaxies define much of the visible structure of the local group. The smaller galaxies are more numerous and more varied. Some are dwarf spheroidal galaxies, faint systems with little gas and mostly old stars. Others are dwarf irregular galaxies with uneven shapes, scattered gas, and ongoing star formation. Their low brightness makes them difficult to detect, especially when they lie near bright foreground stars or behind dense regions of the Milky Way. New surveys continue to reveal small companions whose light is spread so thinly that they remain almost invisible against the sky. The local group has no sharp outer wall. Its boundary is defined mainly by gravity. Near its edges, the attraction of the group becomes comparable to the influence of neighboring groups and the expansion of space. Galaxies within this region tend to move under the combined pull of the local group, while more distant systems follow the larger flow of the universe. This boundary is not perfectly spherical because the group's mass is unevenly distributed. Beyond the local group lie other collections of galaxies The nearest prominent group includes galaxies around Centaurus A and the spiral galaxy Messier 83. Another nearby collection lies in the direction of the Sculptor constellation. These groups are separated from the local group by several million light-years and take part in the broader arrangement of matter known as the cosmic web. Galaxies gather along filaments while large empty regions occupy the spaces between them. The local group itself belongs to a wider region of nearby galaxies, often described as the local sheet. This is a flattened distribution in which many neighboring galaxies share similar motions. The sheet forms part of a much larger network shaped by the gravitational pull of matter over cosmic time. The Milky Way moves within this structure, carried by local attraction and by the larger motion of surrounding galaxy concentrations. The expansion of the universe affects distant galaxies, but gravity dominates inside the local group. The member galaxies do not simply drift apart with cosmic expansion. Their mutual attraction changes their paths. Measurements of light show that Andromeda is moving toward the Milky Way along the line between them. Its sideways motion is smaller and more difficult to measure precisely. Current observations indicate that the two galaxies are on a path that brings them closer over several billion years. The detailed outcome depends on their exact motions, total masses, and the influence of other members. It remains uncertain whether the first close passage leads directly to a merger or to a more extended sequence of encounters. This future motion does not make the local group violent in its present appearance. On human and stellar timescales, its arrangement changes with extreme slowness. The galaxies remain separated by vast regions where matter is very thin. Their stars do not fill the spaces between them. Even within a galaxy, stars are widely separated, and between galaxies the emptiness is greater still. Light crossing the local group carries a layered record of time. The Milky Way is seen from within, while Andromeda appears through light more than 2 million years old. More distant dwarf galaxies are also observed in the past, with the delay set by their distance. The group is therefore never seen at a single shared moment. Its structure is assembled from light that leaves different places at different times. From the outermost view, the Milky Way is one luminous system among many small companions and two other major spirals. Its position is defined by motion, gravity, and relation rather than by a fixed center of the universe. The local group has a center of mass, but that point shifts as its members move and interact. The Milky Way travels through this quiet region with its stars, gas, dust, and unseen mass bound together, while the surrounding galaxies continue their slow paths through the dark expanse. Beyond the disk of the Milky Way, gravity continues through a region that cannot be seen directly. This domain is called the dark matter halo. It surrounds the visible galaxy on every side and extends far beyond the stars, gas, and dust that form the spiral shape. Although the halo gives off no light, its presence becomes clear through the motions of matter that can be observed. Stars, gas clouds, satellite galaxies, and stellar streams all move as though they are responding to much more mass than the visible galaxy contains. Dark matter is the name given to matter that interacts strongly through gravity, but does not appear to emit, absorb, or reflect ordinary light. Its physical nature remains unknown. Observations indicate that it is not made mainly of faint stars, cold planets, ordinary gas, or dust. Those forms of matter consist of atoms and would leave measurable effects through radiation, heat, or chemical signatures. The dark matter halo appears to be composed mostly of a different form of matter that has not yet been identified in laboratory experiments. The halo does not resemble the thin galactic disk. The disk is flattened because gas loses energy through collisions and settles into an orbiting plane. Dark matter does not appear to lose energy in the same way. It remains distributed through a much larger, roughly rounded volume. The exact shape is uncertain. Some measurements suggest a nearly spherical halo, while others allow a mildly stretched or uneven form. The distribution may also change with distance from the galactic center. Evidence for the halo begins with the rotation of the Milky Way. Stars and gas orbit the center under gravity. If most of the galaxy's mass were concentrated in the visible disk and central regions, orbital speeds would gradually decline at large distances. Instead, measurements show that stars and gas far from the center continue moving at unexpectedly high speeds. Their motion indicates that additional mass is spread through the outer galaxy. This unseen mass supplies the gravity required to keep these distant objects in their orbit. The same pattern appears in many other spiral galaxies. Their outer stars also move more rapidly than visible matter alone can explain. Studies of galaxy clusters, gravitational lensing, and the early universe provide further evidence that dark matter forms a large share of cosmic matter. Gravitational lensing occurs when mass bends the path of light passing nearby. The effect follows the geometry of gravity and can reveal matter that produces little or no light. In distant galaxy clusters, lensing maps show large amounts of mass beyond the visible galaxies and hot gas. Within the Milky Way, lensing can sometimes reveal compact objects, but observations show that such bodies cannot account for most of the halo. The main component remains diffuse and invisible. The total mass of the Milky Way is difficult to measure because the outer halo has no clear edge. Estimates commonly place the galaxy's mass near 1 trillion times the mass of the Sun, though significant uncertainty remains. Most of this mass is believed to be dark matter. The visible stars, gas dust planets, and compact objects contribute only a smaller fraction. The exact value depends on how distant stars and satellite galaxies are moving and on assumptions about the halo's shape. The halo's outer boundary is often described through a region where the galaxy's gravity organizes matter into a shared structure. This boundary may extend several 100,000 light-years from the center. It is not a solid surface. Density declines gradually outward, and the Milky Way's influence blends into the gravitational environment of the local group. Dark matter density is not uniform. Models generally indicate that it becomes greater toward the galactic center and lower towards the outer edge. The exact central pattern remains uncertain because visible matter also contributes strongly to gravity in the inner galaxy. In the outer regions, dark matter dominates more clearly. Small concentrations may also exist within the halo. These clumps are expected from computer simulations of galaxy formation, though many may contain few stars and remain difficult to detect. The halo develops over billions of years as smaller structures gather under gravity. In current cosmological models, dark matter begins forming clumps before ordinary gas settles into galaxies. Gas falls into these gravitational wells, cools, and eventually forms stars. The Milky Way grows within such a structure through gradual accumulation and repeated mergers with smaller systems. The present halo therefore carries the combined mass of many earlier fragments. As smaller galaxies enter the Milky Way's gravitational region, dark matter shapes their paths. Some companions remain bound on long orbits, others lose stars and gas through tidal forces. Their own dark matter may be stripped away first because it extends farther from their centers than their stars. This process slowly changes both the satellite and the larger halo. Much of the incoming material spreads into broad streams that become increasingly difficult to distinguish. Stellar streams provide one way to study the halo's gravity. These narrow paths of stars form when a globular cluster or dwarf galaxy is stretched apart. The stars continue along related orbits, tracing the gravitational field through which they move. Small changes in their paths can reveal the overall shape of the halo or suggest encounters with unseen clumps. The measurements remain challenging because the stars are faint, their distances are uncertain, and the Milky Way's visible components also affect their motion. Satellite galaxies offer another measure. Their speeds and positions depend on the mass enclosed within their orbits. A satellite moving rapidly at a great distance requires a strong gravitational hold if it is to remain bound. By combining many such measurements, astronomers estimate the halo's total mass. The result still varies because some satellites may be arriving for the first time, while others have completed several passages. The dark matter halo is quiet in appearance but active through gravity. It guides the rotation of the disk, influences the paths of companions, and provides the main gravitational framework of the Milky Way. No image shows its particles directly. Its form emerges from motion, from bent light, and from the structure of the galaxy as a whole. Around the luminous spiral, the unseen halo remains broad, massive, and gradually thinning into the surrounding space. Around the Milky Way, beyond most of its visible stars, lies an enormous region filled with gas that cannot be seen directly. This region is known as the circumgalactic medium. It surrounds the galaxy in an extended atmosphere and occupies much of the space between the bright disk and the farthest reaches of the galactic environment. The gas is not arranged as a smooth shell. It forms a changing mixture of hot plasma cooler clouds, moving streams, and diffuse material shaped by gravity radiation and the history of the galaxy. The circumgalactic medium contains ordinary matter made of atoms, but most of those atoms are widely separated. In its hottest parts, the gas reaches temperatures of hundreds of thousands or millions of degrees Celsius. At such temperatures, electrons are separated from atomic nuclei, creating plasma. Despite the high temperature, the gas is extremely thin, so it does not feel hot. There are too few particles to transfer much heat. The energy of a particle is high, but the density is low. Much of this gas is difficult to detect because it produces only faint radiation. Astronomers often study it by observing distant sources of light behind the Milky Way. As light from a quasar or galaxy passes through the gas, certain atoms and ions absorb specific wavelengths. These absorption patterns reveal the chemical composition, temperature, and motion of material that would otherwise remain invisible. Different ions trace different conditions, allowing the medium to be examined in detail. Observations show that the circumgalactic medium contains hydrogen, helium, oxygen, carbon, silicon, and other elements. Hydrogen and helium formed in the early universe, while heavier elements were produced inside stars and spread through stellar winds and explosions. Their presence far from the disk shows that matter does not remain confined to the regions where stars form. Gas moves outward from the galaxy carrying material that has been altered by stars. The total mass of the circumgalactic medium is uncertain. It may contain a large fraction of the Milky Way's ordinary matter, possibly comparable to or greater than the mass of all the stars in the disk. Measuring it is difficult because the gas is uneven extended and often too faint to map directly. Some portions are hot and diffuse, while others are cooler and denser. Different observing methods detect different components, so estimates must combine many kinds of evidence. The hot component fills a large volume around the galaxy. It emits weak X-rays as charged particles interact. Sensitive space telescopes detect this radiation and also identify absorption lines produced when background light crosses the plasma. These observations indicate that hot gas extends tens or perhaps hundreds of thousands of light years from the galactic center. Its exact size, density, and shape remain uncertain because emission from the solar system and the wider universe can overlap with the same signals. Within the hot, medium cooler clouds also exist. Some contain neutral hydrogen, meaning that electrons remain attached to hydrogen nuclei. These clouds can be detected through radio emission at a characteristic wavelength. Many move at speeds that do not match the regular rotation of the galactic disk. They are therefore called high-velocity clouds. Their origins vary. Some may be fragments of smaller galaxies, some may be gas falling towards the Milky Way, and others may be material pushed outward by energetic events. The circumgalactic medium is therefore both a reservoir and a pathway. Gas can enter from the wider environment under gravity. As it approaches the galaxy, it may slow cool and mix with material already present. If it loses enough energy, some of it can move inward and eventually become available for star formation. This supply is important because stars continually lock gas into long-lived objects or return part of it through winds and explosions. Matter also travels in the opposite direction. Supernovae, stellar winds, and radiation can heat gas and drive it away from regions of active star formation. In the Milky Way, these outflows may rise above and below the disk into the surrounding medium. Some gas may later cool and fall back, creating a cycle sometimes described as a galactic fountain. Other material may travel farther and remain in the halo for long periods. The balance between inflow and outflow changes over time. Chemical composition helps trace this circulation. Gas enriched with oxygen, carbon, and other heavy elements usually carries evidence of stellar processing. More chemically primitive gas may have spent less time inside galaxies. In practice, the two kinds of material often mix. This makes simple classifications difficult. Observations indicate that the circumgalactic medium contains both recycled galactic matter and material drawn from outside the Milky Way. The gas is influenced by the galaxy's gravity, but gravity is not the only force shaping it. Pressure from hot plasma, magnetic fields, radiation, and interactions between moving clouds all affect its structure. A cool cloud crossing hotter gas may be compressed, stretched, or gradually dissolved. Turbulence can mix materials of different temperatures and compositions. These processes occur over large distances and long periods, producing boundaries that are irregular rather than sharp. The circumgalactic medium also interacts with nearby satellite galaxies. As a small galaxy moves through the Milky Way's surrounding gas pressure can remove some of its own gas. Tidal forces may pull material away at the same time. Long streams of hydrogen can then form across the outer environment. The Magellanic Stream is a prominent example extending across a large part of the sky. Its structure reflects interactions involving the Magellanic Clouds, the Milky Way's gravity, and the gas. Radiation from the Milky Way affects the medium as well. Ultraviolet light from young stars can ionize nearby gas, while energetic events near the central regions may send radiation farther outward. The strength and direction of this influence vary. Some clouds remain partly neutral, while others are highly ionized. Their states depend on temperature, density, distance, and exposure to radiation. From this broad region, the Milky Way appears wrapped in a faint, active atmosphere of ordinary matter. The gas holds a record of material entering, leaving, cooling, heating, and mixing across cosmic time. It is nearly invisible, yet it connects the luminous galaxy with its surrounding environment. Through absorption, X-rays, radio emission, and measured motion, its quiet structure becomes gradually known. Beyond the bright disk of the Milky Way, many smaller galaxies move through its gravitational domain. These satellite galaxies are bound companions, each following a path shaped by the mass of the larger galaxy and by the influence of other nearby systems. Most are faint, small, and widely scattered. Some contain millions of stars, while others hold only a few thousand clearly detected members. Their light is often so weak that they appear as slight increases in the number of stars across a patch of sky. The largest satellites visible from the southern hemisphere are the Large Magellanic Cloud and the Small Magellanic Cloud. They are irregular galaxies rich in gas young stars and active regions of star formation. Their shapes show the effects of gravity and motion. The two clouds influence one another and both respond to the pull of the Milky Way. Their exact orbital history remains under study, but observations indicate that they may be making an early close passage through the outer galactic environment rather than repeating the same orbit over many cycles. Many other satellites are dwarf spheroidal galaxies. These systems have rounded forms, little remaining gas, and stellar populations dominated by old stars. They produce little new starlight because the material needed for star formation has largely disappeared. Their stars move slowly through broad, diffuse structures held together by gravity. Measurements of those motions indicate that dwarf spheroidal galaxies contain much more mass than their visible stars alone can provide. They are therefore important places for studying the effects of dark matter on small scales. Some satellites are called ultra-faint dwarf galaxies. Their total brightness can be lower than that of a single large star cluster though their stars are spread across a much wider region. They are difficult to find because foreground stars from the Milky Way lie in the same directions. Wide surveys identify them by searching for groups of stars with similar colors, distances and motions. As instruments become more sensitive, the known population continues to grow, especially in regions of the sky that were previously examined less deeply. Satellite galaxies do not remain unchanged as they travel. The Milky Way exerts tidal forces differences in gravity across the width of each companion. The near side feels a slightly stronger pull than the far side. Over time, this difference can stretch the satellite and remove stars from its outer parts. The stars do not immediately scatter in every direction. They continue along related orbits and form long, narrow structures known as stellar streams. A stellar stream can extend across tens of thousands of light years while remaining only a few hundred light years wide. Its stars share a common origin even after they become widely separated. Their chemical compositions, ages, and motions often reveal that they once belonged to the same smaller galaxy or star cluster. Some streams are broad and complex, showing that they came from dwarf galaxies with many stars and dark matter. Others are thin and delicate, suggesting an origin in compact, globular clusters. The Sagittarius dwarf spheroidal galaxy provides one of the clearest examples of this process. It is being pulled apart as it moves around the Milky Way. Its stars form extensive streams that wrap around the galaxy in more than one direction. These streams pass through large areas of the sky and contain evidence of repeated stripping during earlier orbital passages. Their shape helps astronomers examine the Milky Way's gravitational field over great distances. The Magellanic Clouds also leave extended structures. Gas drawn from them forms the Magellanic Stream, while stars and gas in other nearby features reflect a long history of interaction. The stellar component is harder to trace than the gas because it is faint and mixed with foreground stars. Observations indicate that gravity between the clouds and the Milky Way, along with pressure from surrounding gas, contributes to the present form of these structures. The relative importance of each process remains uncertain. Streams do not form static lines. Every star continues to orbit the Milky Way, and the entire structure changes slowly with time. Stars stripped earlier move farther from the surviving remnant, while newly removed stars remain closer. This arrangement preserves a record of the satellite's path. By measuring positions, distances, speeds, and chemical patterns, astronomers reconstruct parts of the orbit and estimate when the disruption occurs. The shape of a stream also responds to uneven gravity. A perfectly smooth and simple galactic field would guide the stars along a regular path. In reality, the disk central mass, dark matter halo satellite galaxies and smaller concentrations all contribute. Encounters with massive objects can create gaps, bends, or changes in density. Some disturbances may come from visible structures, while others may reveal dark objects with few or no stars. The evidence is delicate, and several causes can produce similar patterns. Not every satellite is being rapidly destroyed. Some remain compact and may continue orbiting for billions of years. Their survival depends on their mass, internal structure, distance from the Milky Way, and past encounters. A satellite passing close to the galactic center experiences stronger tides than one remaining far away. Repeated passages can gradually remove its outer material, reducing its mass and changing its orbit. The present collection of satellites is therefore only part of a longer history. Some companions merge completely and lose their separate identity. Their stars spread into the Milky Way's outskirts, where they retain traces of their origin through motion and chemistry. Other satellites may have been destroyed so long ago that only broad, faint structures remain. The outer galaxy contains many such remnants layered across one another and difficult to separate. Satellite galaxies and stellar streams reveal that the Milky Way is not surrounded by empty space. It is accompanied by smaller systems in different stages of survival, disruption, and absorption. Their stars move quietly through wide arcs, carrying evidence of earlier structures and long gravitational encounters. Across the outer galactic environment, the remnants of these companions form a changing map of motion, linking the Milky Way to the smaller galaxies that continue to shape its extended form. Even the faintest stream preserves a quiet record of where its parent system travels, how strongly gravity pulls, and how slowly a galaxy gathers material across immense cosmic time. Far beyond the crowded stellar disk, the Milky Way contains a broad and faint population known as the outer stellar halo. This region is not a smooth band of light. Its stars are thinly scattered through a vast volume with enormous distances separating one small concentration from another. Most are old and many contain fewer heavy elements than stars born later in the galactic disk. Their motions, compositions, and distribution preserve evidence of the earliest stages of the Milky Way's growth. The stellar halo differs from the dark matter halo that surrounds it. Dark matter provides most of the mass and remains invisible, while the stellar halo contains ordinary stars that can be observed directly. The stars contribute only a small fraction of the galaxy's total mass, yet they offer clear records of past events. They orbit in many directions rather than following the orderly rotation of the disk. Some move on long stretched paths that carry them far above or below the galactic plane. Many halo stars are described as metal poor. In astronomy, a metal is any element heavier than hydrogen or helium. The earliest generations of stars form from gas containing few of these heavier elements because most metals have not yet been created. As stars live and die, they produce carbon-oxygen ion and many other elements, enriching later clouds of gas. A metal-poor star, therefore, often formed when the universe and the Milky Way were chemically younger. The exact age of an individual halo star can be difficult to determine, but many are more than 10 billion years old. Some formed before the Milky Way developed its present spiral disk. Their atmospheres retain the chemical pattern of the gas from which they formed. By measuring the strength of absorption lines in starlight, astronomers estimate the abundance of iron and other elements. These measurements reveal differences between stars born in the early Milky Way and stars later added from smaller galaxies. The outer halo contains a mixture rather than a single population. Some stars may have formed within the early Milky Way, while many others entered through mergers. A smaller galaxy falling into the Milky Way can be stretched and disrupted. Its stars continue along related orbits and gradually spread through the halo. After several billion years, the original galaxy may no longer remain visible, but groups of stars can still share similar motion and chemistry. This process gives the halo a layered structure. Some features appear as narrow streams, while others form broad cloud shells or overlapping regions. A collection may be difficult to recognize in ordinary images because its stars are widely dispersed. Precise measurements of position and motion can reveal that stars separated across the sky once belonged to the same system. Chemical similarities provide another connection, especially when several elements show matching patterns. Globular clusters are among the most prominent objects in the stellar halo. A globular cluster is a dense, nearly spherical gathering of old stars bound by gravity. The Milky Way contains more than 100 known clusters, and many travel far from the disk. Their centers can hold thousands of stars within a relatively small region, while their outer stars form a more diffuse boundary. Most globular clusters contain stars that formed at nearly the same time from related material. This makes them valuable for estimating age and studying stellar evolution. The stars differ mainly in mass, so their present brightness and temperature show how stars of different masses change over time. Some clusters are almost as old as the Milky Way itself. Their ages place important limits on when the galaxy begins assembling its earliest structures. Globular clusters are not all chemically identical. Some are extremely metal-poor, while others contain more heavy elements. Certain clusters also contain several stellar populations with subtle chemical differences. This indicates that their formation histories can be more complex than a single brief event. In some cases, a massive cluster may be the surviving central region of a dwarf galaxy that loses its outer stars. The origin of several unusual clusters remains under study. The orbits of globular clusters help map the outer galaxy. Some follow wide inclined paths, and others move on highly elongated orbits. Their speeds respond to the total gravitational field, including the dark matter halo. By combining their motions with those of halo stars and satellites, astronomers estimate how mass is distributed far from the galactic center. Uncertainty remains because the most distant objects require precise measurements across immense distances. Individual halo stars are often identified through their speed direction and chemical composition. A star passing near the solar system can belong to the halo, even though it is temporarily moving through the disk. Its orbit may carry it far outside the plane before returning. Such stars often move differently from nearby disk stars, crossing local space on steep or backward paths. Their presence shows that the halo extends through the disk rather than beginning at a sharp boundary. Some of the most metal-poor known stars contain only tiny amounts of iron. Their chemistry provides clues about the first generations of stellar explosions. These ancient stars are not necessarily the very first stars, because the first stars are expected to have formed almost entirely from hydrogen and helium and to have ended their lives long ago. The oldest surviving stars likely formed from gas lightly enriched by those earlier stars. Their abundance patterns help test models of early star formation and nucleosynthesis, the creation of elements inside stars, and stellar explosions. The density of halo stars decreases with distance from the Milky Way. Near the inner regions, overlapping debris and older populations create a more complex structure. Farther outward stars become increasingly rare and individual streams or clusters stand against an empty background. The outer halo has no perfectly defined edge. Its faint population gradually blends into the wider environment where satellite galaxies and isolated stellar remnants continue their motion. Seen through its ancient stars, the outer halo is a quiet archive. It records small galaxies absorbed long ago, clusters that survive repeated passages, and early stars formed from nearly pristine gas. Its light is weak, but its history is deep. Across the darkness, each orbit and chemical pattern adds another trace to the long assembly of the Milky Way. At the distant edge of the Milky Way's visible disk, the orderly shape of the galaxy becomes thinner, fainter, and less regular. The outer disk does not continue as a perfectly flat sheet. Instead, it bends above and below the central plane in a broad structure known as the galactic warp. This bending is gentle across immense distances, but it becomes clear when hydrogen gas and distant stars are mapped around the galaxy. The warp shows that the disk is not a rigid surface. It is a moving collection of stars and gas responding to gravity from many directions. The inner disk remains comparatively flat because its stars and gas are densely concentrated and strongly bound within the main gravitational plane. Farther outward, the material becomes more weakly held and more easily disturbed. The outer disk contains fewer stars, less gas, and a lower overall surface density. Small gravitational influences can therefore produce larger changes in its shape. The bending begins gradually and becomes stronger with increasing distance from the galactic center. Neutral hydrogen provides one of the clearest maps of this region. Neutral hydrogen is hydrogen gas, in which electrons remain attached to their nuclei. It emits radio waves at a characteristic wavelength, allowing astronomers to trace gas even where starlight is scarce or hidden by dust. These radio observations show that the hydrogen layer rises above the central plane on one side of the galaxy and falls below it on the other. The cause of the warp remains under study. Several influences may contribute. The gravitational pull of the Magellanic Clouds can disturb the Milky Way's outer regions, especially because the clouds move through the surrounding dark matter and gas. The dark matter halo itself may be slightly tilted or uneven relative to the disk. Gas entering from the wider galactic environment can also apply pressure or bring angular momentum that differs from the motion of the disk. Observations indicate that no single, simple explanation accounts for every measured feature. The warp is not fixed in space like a bent plate. Stars and gas continue orbiting the galactic center while the pattern changes slowly. Different rings of material can tilt by different amounts, creating a twisted outer structure. The rate and direction of this motion depend on the distribution of mass throughout the Milky Way. Because the outer disk takes hundreds of millions of years to complete an orbit, even gradual changes persist across long periods. Along with the warp, the outer disk displays a flare. A flare is a gradual increase in the thickness of the disk with distance from the center. Nearer the main stellar regions, many stars remain close to the central plane. Farther outward, their vertical motions carry them over a broader range above and below it. The disk, therefore, becomes thicker, even as its total density declines. This flaring appears in several stellar populations and in the gas layer. The flare develops partly because gravity becomes weaker in the outer disk. With less mass pulling stars tightly toward the central plane, the same amount of vertical motion carries them farther away. Gravitational disturbances can also increase random stellar motion and expand the layer. Passing satellite galaxies, spiral patterns, and uneven mass distributions may all contribute. Stars in the outer disk are sparse compared with those closer to the center. Large distances separate many stellar groups, and the surface brightness falls to levels that are difficult to distinguish from foreground and background light. Some stars form extended rings or uneven concentrations rather than a smooth continuation of the inner disk. Determining which features truly belong to the disk and which come from disrupted satellites requires careful measurements of distance motion, age, and chemical composition. Outer disk stars often contain fewer heavy elements than stars formed closer to the galactic center. This pattern reflects the history of gas enrichment. In regions with frequent star formation, repeated generations of stars return heavy elements to surrounding gas. In the outer disk, star formation is weaker and more scattered, so enrichment proceeds more slowly. The chemical difference is not perfectly uniform because gas moves across the galaxy, and stars can change their orbital distances over time. The gas in this region is mostly thin and cool compared with the hot material surrounding the galaxy. Large areas contain atomic hydrogen at low density. Molecular gas, which consists mainly of hydrogen molecules, is less common because molecules form more easily in denser, dustier environments. Without enough shielding from ultraviolet radiation, molecular clouds are difficult to maintain. Star formation therefore occurs only where local compression creates conditions dense and cold enough for gravity to gather material. Even at these distances, small pockets of young stars exist. Their presence shows that the outer disk is not entirely inactive. Some form in isolated clouds far from the bright bands of the inner galaxy. These regions usually produce fewer massive stars and smaller stellar groups. Their faint light and great distance make them challenging to observe, especially through the dust and crowded sight lines of the galactic plane. Dust also becomes less abundant toward the outer disk, though it does not disappear. Grains of carbon-rich and silicon-rich material mix with the gas and absorb or scatter starlight. Lower metal abundance means that fewer solid grains are available to help cool clouds and protect molecules. This changes how gas collapses and may affect the kinds of stellar nurseries that develop. Observations continue to refine this complex relationship across the region over time. The outer disk does not end at one sharp radius. Different traces fade at different distances. Bright young stars become rare before neutral hydrogen disappears. Old stars can extend beyond regions where active star formation is easily detected. Faint structures may continue farther than early surveys indicate, while some apparent edges reflect limits in sensitivity rather than physical boundaries. Across this warped and flaring region, the Milky Way becomes increasingly delicate in appearance. Its disk bends, thickens, and thins as stars and gas follow broad orbits under an uneven gravitational field. The outer rim remains part of the galaxy, but its structure is loose, faint, and responsive. In its slow curvature and scattered light, the disk reveals that even a vast spiral system is flexible, shaped continuously by motion, gravity, and the matter around it. Beyond the warped rim of the main stellar disk, the Milky Way continues through faint, outer spiral regions where stars and gas gather into uneven patterns. They are areas where material becomes slightly more concentrated as it moves around the galactic center. From within the galaxy, the arms are difficult to trace because dust, distance, and overlapping stars hide their full form. Spiral arms are patterns rather than permanent collections of the same stars. Stars enter and leave these regions as they orbit, while gas can be compressed and slowed within them. The mechanism maintaining the Milky Way's spiral structure remains uncertain. Density, waves, gravitational disturbances, and interactions with smaller galaxies may all contribute. In the outer disk, these influences become weaker and less regular, producing arms that appear fragmented, stretched, or discontinuous. The Milky Way contains several named spiral features, but their boundaries are not sharply defined. In the outer regions, the outer arm is one of the most distant recognized structures. It curves around the galaxy beyond the Sun's position and contains atomic gas, molecular clouds, young stars, and scattered star-forming regions. Radio measurements are especially important because they pass through dust that blocks visible light. Neutral hydrogen outlines much of the outer spiral pattern. Its radio emission allows astronomers to estimate the speed of gas along different lines of sight. By combining those speeds with models of galactic rotation, the gas can be placed approximately within the disk. This method is uncertain because gas does not always follow circular paths. Warping, streaming motions, and local disturbances can shift the infrared position of a cloud by large distances. Molecular gas is less common than atomic hydrogen in these distant regions. Molecules form and survive most easily where gas is dense, cold, and protected from ultraviolet light. Dust grains help by providing surfaces on which hydrogen atoms can combine. Since the outer disk contains less dust and fewer heavy elements, molecular clouds are generally smaller, more isolated, and more difficult to detect. Carbon monoxide is often used as a tracer of molecular hydrogen, but it becomes faint where metal abundance is low. Some outer clouds may therefore contain molecular hydrogen that is not easily revealed by standard observations. This material is sometimes described as carbon monoxide dark gas. Its presence is inferred through dust emission gamma rays or other chemical traces. The amount remains uncertain, but it may add significantly to the known gas supply in the outer spiral regions. These hidden molecules show that low brightness does not always mean an absence of cold material. Star formation occurs where portions of a cloud become dense enough for gravity to overcome internal pressure turbulence and magnetic support. In the outer arms, such conditions are less frequent than in the inner disk. The gas surface density is lower and the clouds are more exposed to radiation. Even so, young stars and compact nebulae appear in scattered groups. Their existence shows that stellar birth continues far from the crowded central regions. Many outer star-forming sites contain only modest numbers of young stars. Massive stars are present in some locations, and their ultraviolet radiation ionizes nearby hydrogen, creating faint, glowing regions. These areas can be mapped through radio waves and infrared light even when visible light is heavily obscured. The young stars often remain close to the gas from which they form because they have not had enough time to travel far along their orbits. The chemistry of these regions differs from that of the inner galaxy. Gas farther from the center usually contains fewer elements heavier than hydrogen and helium. This affects cooling dust formation and the structure of molecular clouds. Lower metal abundance reduces the number of atoms and grains that can radiate energy efficiently. Clouds may therefore require different conditions before collapsing. Observations indicate that star formation remains possible, but its efficiency and detailed behavior vary from place to place. The outer arms also contain older stars that did not necessarily form there. Stellar orbits can change through interactions with spiral patterns, the galactic bar, or passing satellites. This movement, called radial migration, shifts a star's average distance from the center without violent scattering. Some stars now found in the outer disk may have formed farther inward and moved outward over billions of years. Others remain close to their birthplaces. Because the outer disk is warped, a spiral arm may rise above or fall below the central plane. This geometry complicates maps drawn from the Sun's location. A cloud that appears far above the plane may still belong to the warped disk rather than to the halo. Astronomers use stellar brightness parallax, maser emission, and gas motion to build a three-dimensional picture. Masers are intense, narrow radio signals produced under special conditions in molecular clouds and regions around young stars. Very long baseline observations can measure their positions with extraordinary precision. Repeated measurements reveal parallax, the slight apparent shift caused by Earth's orbit and motion across the sky. These data provide some of the clearest distances to remote star-forming regions and help trace the curve of spiral arms. The outer spiral regions are not perfectly symmetrical. One side of the galaxy may contain more gas or stronger structure than another. The distribution changes under the influence of the warp-satellite interactions and uneven inflow from the surrounding environment. Over long periods, spiral features may weaken and reform as the disk responds to changing gravitational forces. At these distances, an arm is less a bright river of stars than a faint gathering of gas and scattered stellar light. Long intervals of darkness separate small nurseries and loose associations. Radio emission reveals hydrogen where the eye would see almost nothing. Infrared observations uncover warm dust and young stars hidden inside clouds. Together, these signals show that the Milky Way's spiral form continues into regions where matter is sparse and the pace of change is slow. The outer arms carry material around the galaxy in broad orbits lasting hundreds of millions of years. Clouds gather, cool, fragment and disperse while stars emerge and gradually leave their birth regions. The pattern remains incomplete and uneven, shaped by gravity without becoming fixed. Across the distant disk, the spiral structure persists as a quiet arrangement of cold gas, faint stars and isolated places where new light begins. The solar neighborhood lies within a spiral feature called the Orion Spur, a bridge of stars and gas between larger spiral arms. It is not a bounded region, and its limits depend on the kind of object being studied. From this position, the Milky Way appears as a band across the sky, because the line of sight passes through the plane of the disk. Nearby stars seem scattered in every direction, yet most belong to the same rotating structure that carries the Sun around the galactic center. The Orion Spur contains a mixture of old stars, young stellar groups, diffuse gas dust clouds, and the remains of stellar activity. It is smaller than the major spiral arms and may be partly shaped by their gravitational influence. The Sun is located roughly halfway between the galactic center and the outer edge of the visible disk, though the exact distance depends on how the center and disk boundary are defined. Its position places it within a quiet part of the local environment. The Sun moves around the galactic center along an orbit that is nearly circular, but not perfectly so. One complete orbit takes more than 200 million years. During that time, the Sun also moves inward and outward and rises above and below the central plane. These motions are gentle compared with the size of the galaxy. Nearby stars follow their own paths, and their relative positions change over thousands and millions of years. The local standard of rest is a reference describing these motions. It represents the average circular motion of stars near the Sun. The Sun moves slightly differently from that average, so nearby stars appear to drift across the sky with a combination of their own motion and the Sun's. Precise measurements of position, distance, and velocity reveal that the solar neighborhood is not a fixed arrangement. It is a temporary gathering of stars passing through the region. Parallax provides the most direct way to measure the distances of nearby stars. As Earth travels around the Sun, a nearby star appears to shift slightly against more distant background objects. The size of this shift gives its distance. Modern space observatories measure changes across the sky and determine the positions and motions of many stars. These data show the local disk as a dynamic structure with streams, clusters, and populations of different ages. The nearest stellar system is Alpha Centauri, a group of 3 stars located more than 4 light-years away. Other nearby stars include Barnard's star Sirius, Epsilon Eridani, and several faint red dwarfs. Red dwarfs are small, cool stars that burn their fuel slowly and remain active for long periods. They are the most common stars in the galaxy, yet many are difficult to see without telescopes because their light is weak. The brightest stars in the night sky are not always the nearest. Some appear bright because they are intrinsically luminous, while others are close enough for their modest light to seem strong. Sirius is both nearby and luminous, making it bright. Large blue stars can be visible across greater distances, but they live for shorter periods. The local population, therefore, contains many faint, long-lived stars and a smaller number of bright, short-lived ones. Several nearby stellar associations preserve evidence of recent star formation. An association is a loose group of stars born from related clouds but not tightly bound together. Over time, its members drift apart. The Scorpius-Centaurus Association is one of the nearest large groups of young stars. Its massive members produce strong radiation winds and supernova explosions that shape the surrounding gas. Their influence extends across a wide part of the local environment. The solar neighborhood also contains the local bubble, a low-density cavity in the interstellar medium. It extends for hundreds of light-years in some directions and has an irregular shape. The cavity contains hot, thin gas and is bordered by denser clouds and shells. Evidence indicates that several supernova explosions help create and enlarge this region over millions of years. The Sun currently travels through a smaller cloud of partially ionized gas within the cavity. The local gas is thin by terrestrial standards. Even within a cloud, atoms can be separated by distances large compared with their own size. Dust grains are rarer still, yet they have a strong effect on light. They absorb and scatter shorter wavelengths, dimming distant stars and creating dark patches against the Milky Way. Infrared observations reveal warmer dust and embedded young stars that visible light cannot reach. Nearby molecular clouds form some of the clearest local star-forming regions. The Taurus molecular cloud contains cold gas and many low-mass young stars. The Orion molecular cloud is more active and includes massive stars, glowing nebulae, and dense regions where new stars continue to form. These clouds are not permanent objects. Gravity, turbulence, magnetic fields, radiation, and stellar feedback slowly reshape them. The motions of nearby stars also reveal groups that share a common origin. Moving groups contain stars with similar velocities even when they are spread across a large area. Some are remnants of dissolved clusters. Others may be parts of patterns created by spiral structure or resonances in the disk. Their ages and chemical compositions help determine whether shared motion reflects a common birthplace or only a similar response to galactic gravity. The solar neighborhood contains stars of many ages and chemical histories. Thin disk stars usually follow relatively orderly orbits close to the galactic plane and often contain more heavy elements. Thick disk stars tend to be older, move on less circular paths, and reach greater distances above and below the plane. Halo stars occasionally pass through the same local space on steep, rapid orbits. These populations overlap in position while remaining distinct in motion and composition. Within this local region, the Sun is ordinary in many respects. It is a middle-aged star with a moderate mass and a composition typical of later stellar generations. Its surroundings are neither a dense cluster nor an empty void. They form a quiet part of the Orion spur, where stars, clouds, and diffuse gas share the slow rotation of the disk. Across the solar neighborhood, motion remains constant, structure remains temporary, and the familiar sky gradually changes as each star continues along its own galactic path. The main spiral arms of the Milky Way form broad regions where stars, gas, and dust gather into long curved patterns around the galactic center. They are not solid structures and they do not move as single fixed objects. Instead, they are patterns of increased density through which stars and clouds pass while continuing their orbits. From the solar neighborhood, these arms are seen from within the disk, so their full shape must be reconstructed from many separate measurements. Several major arms are commonly identified, including the Perseus arm, the Scutum Centaurus arm, and the Sagittarius arm. Their names come from the constellations toward which parts of them appear in the sky. The exact number, width, and continuity of the arms remain uncertain because dust blocks visible light and because different tracers reveal different structures. Young stars may outline one path while atomic gas, molecular clouds, and older stars show slightly different patterns. Distances to these regions are measured through several methods. Parallax gives direct distances to nearby Marses and young stars, while gas velocity provides estimates across wider portions of the disk. Each method has limits, so maps combine many observations. The resulting picture shows arms with branches, gaps, and spurs, rather than smooth lines reflecting the changing distribution of matter across the rotating galaxy itself. The Perseus arm lies beyond the Sun's position when viewed away from the galactic center. It contains large clouds of gas, bright stellar nurseries, and groups of massive young stars. Radio observations trace hydrogen across distances where visible light becomes weak. Infrared surveys reveal stars forming inside dust-covered clouds. These methods show that the arm is broad rather than narrow, and that its density changes from one region to another. The Scutum Centaurus arm curves through the inner disk and contains some of the Milky Way's richest star-forming regions. It includes massive stellar complexes where gas collects across hundreds of light years. Within these regions, smaller clouds become dense enough for gravity to pull material inward. The result is not one single event, but a chain of star formation spread across many locations and times. The Sagittarius arm lies closer to the solar neighborhood and contains many bright nebulae visible from Earth. Some of these glowing regions are clouds of hydrogen ionized by nearby hot stars. Ultraviolet radiation removes electrons from hydrogen atoms, and the gas emits light as electrons later rejoin the nuclei. This process creates wide areas of reddish emission, though dust can hide much of the glow at visible wavelengths. Spiral arms are closely linked with gas compression. As gas moves into a denser spiral pattern, it can slow and gather. Clouds collide, turbulence changes, and local pressure increases. These processes can help create cold, dense regions where stars form. The arm does not force every cloud to collapse, and star formation can occur outside the arms, but the concentration of material makes stellar birth more common within them. Molecular clouds are central to this activity. They contain cold gas dominated by molecular hydrogen along with dust and small amounts of other molecules. Their temperatures are often only a few tens of degrees above absolute zero. At such low temperatures, internal pressure is reduced, allowing gravity to influence dense regions more strongly. The largest molecular clouds contain enough material to form thousands or even millions of stars over time, though only a fraction of their gas becomes locked into stars. Inside a molecular cloud structure appears on many scales. Broad filaments of gas divide into denser clumps, and those clumps can fragment into smaller cores. A core may collapse if gravity exceeds the support provided by heat turbulence and magnetic fields. As material falls inward, it forms a young star surrounded by a rotating disk. Jets and winds can emerge from the forming star and remove some surrounding gas. Massive stars form less often than low-mass stars, but they strongly affect the arms. Their intense radiation heats and ionizes nearby gas. Their stellar winds push material outward, creating cavities and shells. Because massive stars live for only a few million years, they remain close to the regions where they form. Their locations, therefore, provide useful markers of recent star formation and help outline the spiral pattern. Groups of young stars often appear as open clusters or loose associations. Open clusters are collections of stars born from the same cloud and held together for a time by gravity. Their members share similar ages and chemical compositions. Over millions or billions of years, gravitational encounters and the pull of the galaxy can scatter them. Loose associations are less tightly bound and disperse more quickly, spreading their stars along the disk. Nebulae within the arms take several forms. Emission nebulae glow because radiation excites or ionizes their gas. Reflection nebulae shine by scattering light from nearby stars. Dark nebulae appear as black shapes because dense dust blocks the light behind them. Supernova remnants form when exploding stars send expanding shock waves into surrounding material. Each type reveals a different part of the continuing exchange between stars and interstellar matter. The arms also contain older stars that simply pass through. A star can enter a spiral region, continue along its orbit, and leave without changing greatly. The visible prominence of an arm comes mainly from bright young stars glowing gas and dust rather than from a very large excess of total stellar mass. This distinction explains why spiral arms can remain recognizable even though individual stars do not remain inside them permanently. The pattern speed of the arms may differ from the orbital speed of stars and gas. This allows material to cross the spiral structure. The exact behavior is complex, and observations indicate that some arm segments may be temporary or may move with different speeds. Rather than forming one perfectly stable design, the Milky Way's arms may grow, weaken, connect and separate over long periods. Across the main spiral arms, the disk becomes a broad system of motion and renewal. Gas gathers into clouds, clouds fragment, stars emerge, and stellar energy returns matter to the surrounding space. Bright nebulae and young clusters mark only the most visible stages of a process that continues through dust and darkness. The arms remain curved regions of increased density, shaped by gravity and motion as the galaxy turns. Within the inner disk of the Milky Way, the spaces between stars are filled with a thin and varied mixture called the interstellar medium. It is not empty space. It contains gas dust, charged particles, magnetic fields, and radiation moving through a broad environment shaped by gravity and stellar activity. Most of the volume is extremely sparse, yet the material is essential to the life of the galaxy. Stars form from it, return matter to it, and alter its temperature, chemistry, and motion. Hydrogen is the most abundant element in the interstellar medium. It appears in several forms depending on temperature, density, and radiation. In some regions, hydrogen atoms remain neutral with electrons attached to their nuclei. In others, energetic light removes the electrons and creates ionized gas. In the coldest and densest clouds, hydrogen atoms join in pairs to form molecules. These different states occupy overlapping regions rather than perfectly separated layers. Neutral atomic hydrogen fills large portions of the disk. It is usually too cool and faint to glow in visible light, but it emits radio waves at a characteristic wavelength. These signals pass through dust and allow astronomers to map gas across the galaxy. The observations show broad clouds, narrow filaments, shells and cavities. Some structures follow the rotation of the disk, while others carry the marks of expanding bubbles, shock waves, and local turbulence. Ionized hydrogen appears where ultraviolet radiation is strong or where gas has been heated by collisions. Around hot young stars, the radiation creates glowing regions in which electrons move freely among atomic nuclei. More diffuse ionized gas extends far beyond the brightest nebulae and fills a significant part of the disk. It is traced through faint emission radio signals and the way free electrons delay certain pulses arriving from distant astronomical sources. Molecular gas gathers in colder and denser regions. The molecules are difficult to observe directly because cold molecular hydrogen produces little radiation. Other molecules, especially carbon monoxide, are used as tracers. Their emission reveals clouds where temperatures are low and densities are higher than in the surrounding medium. These clouds contain complex internal structures including sheets, knots and filaments formed by gravity, turbulence and magnetic forces. Dust forms only a small fraction of the interstellar medium by mass, but it has a strong effect on what can be observed. Interstellar dust consists of tiny solid grains containing carbon-rich material, silicon-rich minerals and traces of ice. In cold environments, the grains absorb and scatter starlight, making distant regions appear dimmer and redder. They also emit infrared radiation after being warmed by nearby stars. The surfaces of dust grains provide places where chemical reactions can occur. Hydrogen molecules form efficiently when atoms meet on these surfaces. In cold clouds, water, carbon monoxide, methane, and other substances can freeze onto grains and create thin, icy coatings. Radiation and collisions slowly change this material, producing more complex molecules. Some of these molecules later enter forming stars and planetary systems as part of the cloud collapses. Cosmic rays also pass through the interstellar medium. They are high-energy atomic nuclei and electrons moving close to the speed of light. Many are accelerated by shock waves from supernova remnants, though other energetic sources may contribute. Cosmic rays penetrate clouds that ordinary ultraviolet light cannot enter. There, they ionize atoms and molecules, beginning chemical reactions and influencing the electrical state of the gas. Magnetic fields extend through the inner disk and connect regions separated by great distances. The fields are weak compared with familiar magnets, but the interstellar medium is so thin and large that their influence becomes important. Charged particles tend to move along magnetic field lines, and clouds can be supported, compressed, or guided by magnetic forces. The fields also affect cosmic rays and help shape filaments, shells, and turbulent motion. Turbulence is common throughout the medium. Gas moves in irregular currents across a wide range of scales. Energy enters through stellar winds, supernova explosions, galactic rotation, gravity, and the motion of clouds. Large disturbances break into smaller ones until their energy becomes heat. Turbulence can prevent some clouds from collapsing while also compressing other parts until gravity becomes stronger. It creates a changing balance rather than a single orderly flow. Supernova explosions have a major influence on the inner disk. When a massive star ends, its life rapidly expanding material pushes into the surrounding gas. The shockwave heats, compresses and accelerates the medium. Over time, the expanding remnant forms a shell around a hotter interior. Several explosions in related stellar groups can combine to produce superbubbles hundreds of light years across. These cavities may break through thinner parts of the disk and carry hot gas away from the central plane. Stellar winds produce smaller bubbles around active stars. Low-mass stars also return matter through slower winds during late stages of their lives. This material contains elements created or rearranged inside stars. Supernovae add heavier elements and spread them more widely. Carbon, oxygen, silicon, iron, and many other elements enter the interstellar medium through these processes, changing the composition of gas available for later stellar generations. The different parts of the medium exchange matter continually. Hot gas cools as it radiates energy. Warm gas can collect into denser clouds. Molecular clouds can be dispersed by radiation winds and explosions. Dust grains can grow in cold regions, break apart in shocks, or be destroyed by intense heat. The boundaries between phases are irregular and active, with material mixing as pressure and temperature change. Pressure helps keep these phases in a rough balance, though the balance is never exact. A hot, thin region can exert pressure comparable to that of a cool, dense cloud because its particles carry more energy. Magnetic pressure, cosmic rays, and turbulent motion add further support. Local events disturb the arrangement, and the medium responds through expansion, cooling, compression, and flow. Across the inner disk, the interstellar medium forms the material framework between stars. It dims distant light, carries magnetic fields, receives the products of stellar evolution, and gathers into clouds under gravity. Its gas and dust remain in constant circulation, moving slowly between warm, cold, hot, neutral, ionized, and molecular states. Though sparse in most places, it binds the visible stages of stellar life into one continuous galactic process across cosmic time. Several thousand light years from the galactic center, the Milky Way contains a broad concentration of cold molecular gas, often called the galactic molecular ring. The name suggests a complete and regular circle, but the structure is more complicated. It may include overlapping spiral arms, elongated streams, and dense cloud complexes seen in projection from the solar neighborhood. Even so, observations show a strong rise in molecular material across this inner part of the disk, making it one of the most active regions for star formation in the galaxy. The ring lies inside the Sun's orbit and outside the crowded central zone. Its exact inner and outer boundaries depend on the tracer used and on the model adopted for galactic rotation. Much of its molecular gas is found between roughly 10,000 and 20,000 light-years from the center. Across this wide band, gas density, cloud mass, and star-forming activity are generally greater than in the outer disk. The region is therefore not a narrow line, but a thick, uneven belt spread through the inner Milky Way. Molecular hydrogen forms most of the gas, yet it remains difficult to observe directly at the low temperatures found in clouds. Astronomers, therefore, map the region mainly through carbon monoxide and other molecules that emit radio waves. These signals pass through dust and reveal cloud velocities along the line of sight. By comparing those velocities with the rotation of the galaxy, researchers estimate where the clouds lie. The method becomes uncertain where several distances produce similar motions, so additional observations are often needed. The molecular ring contains giant molecular clouds, immense structures of cold gas and dust. Some extend across more than 100 light years and contain enough material to form many thousands of stars. Their interiors are not uniform. Broad envelopes surround filaments, clumps, and dense cores. Most of the gas remains too diffuse to collapse at once. Star formation begins only in the smaller regions where gravity becomes strong enough to overcome pressure, turbulence, and magnetic support. Temperatures inside the darker parts of these clouds can fall to only a few tens of degrees above absolute zero. At such low temperatures, atoms and molecules move slowly, reducing thermal pressure. Dust blocks much of the ultraviolet radiation that would otherwise break molecules apart. The same dust also radiates faintly in infrared and sub-millimeter wavelengths, providing another way to trace cold material hidden from visible light. The clouds move through a region shaped by the Milky Way's rotation and by the gravitational influence of spiral structure. Gas entering a denser spiral pattern can become compressed, increasing the chance that clouds merge or fragment. Shear the difference in orbital speed across a cloud can stretch material and oppose collapse. The result is a balance between forces that gather gas and forces that pull it apart. No cloud remains unchanged for very long on galactic timescales. Star formation in the molecular ring occurs in clusters, associations, and extended complexes. Dense cores collapse and form protostars, young objects still gathering material. Rotating disks develop around many of them, while jets and outflows carry some gas away. As the stars grow, their radiation begins to heat the surrounding dust. Infrared observations reveal these embedded stages before the stars become visible through the cloud. Massive stars have a particularly strong influence. They emit intense ultraviolet radiation, creating expanding regions of ionized hydrogen. Their winds push against nearby gas and carve bubbles through the cloud. After a few million years, some end in supernova explosions that send shock waves into the surrounding medium. These events can compress parts of a cloud, but they can also disperse the material and halt further star formation nearby. Their effects depend on density, geometry, and timing. The ring contains some of the Milky Way's most luminous star-forming complexes. These regions include many young massive stars, bright radio sources, warm dust, and dense molecular clumps. Visible light often fails to reach them because dust absorption is severe along the inner galactic plane. Radio and infrared telescopes, therefore, provide the clearest view. Different wavelengths trace different stages, from cold clouds to heated dust and ionized gas. Chemical observations reveal a rich mixture of molecules. Along with carbon monoxide, clouds contain ammonia, formaldehyde, methanol, and many other compounds. These substances form through reactions in the gas and on the surfaces of dust grains. Their emission lines act as thermometers and density probes. Some molecules are common in cold, quiet gas, while others become abundant near shocks, young stars, or heated cores. The abundance of heavy elements is generally higher here than in the outer disk. Earlier generations of stars have enriched the gas with carbon, oxygen, nitrogen, silicon, and iron. More heavy elements allow more dust to form and provide efficient ways for clouds to cool. This environment supports large molecular complexes, though high density also increases the rate of collisions, feedback, and disruption. Gas does not remain in the ring permanently. Galactic rotation carries clouds around the center, while gravitational torques and spiral patterns change their paths. Some material moves inward over long periods, and some is pushed outward or dispersed. Stars born in the region gradually separate from their parent clouds and continue on individual orbits. The molecular concentration is therefore a continuing pattern of supply compression, collapse and dispersal rather than a fixed collection of the same matter. Its many cloud complexes remain separated by warmer interstellar regions, so the belt appears as a broken concentration rather than a continuous wall of gas. Measurements of the ring also help reveal the structure of the inner Milky Way. Because much of the region lies behind thick dust, molecular emission becomes a map of otherwise hidden space. Cloud velocities show how gas responds to the central bar and spiral arms. Regions of unusually strong emission mark places where material gathers, while gaps may reflect changing orbital paths or limited sensitivity. Across this broad inner belt, cold matter becomes concentrated into some of the galaxy's largest clouds. Within them, darkness holds dense networks of gas and dust where new stars form slowly and unevenly. Radiation winds gravity, magnetic fields, and turbulence reshape every cloud. The galactic molecular ring remains a crowded reservoir carrying the raw material of future stars through the rotating inner disk. Inside the galactic molecular ring, the Milky Way's structure becomes dominated by a long concentration of stars known as the central bar. Rather than forming a circular arrangement around the middle of the galaxy, this region stretches across the inner disk in an elongated shape. Its stars move along organized but complex paths, creating a stellar structure that rotates as a pattern. The bar influences the motion of gas dust and stars across thousands of light years, making it one of the important gravitational features in the inner Milky Way. The central bar cannot be viewed directly as a complete shape because the solar neighborhood lies inside the galactic disk. Dense dust blocks much of the visible light from the inner regions, while foreground stars overlap with more distant populations. Infrared observations provide a clearer view because infrared light passes through dust more easily. Star counts, brightness measurements, and stellar motions reveal an elongated concentration, tilted relative to the line between the Sun and the galactic center. Measurements indicate that the nearer end of the bar lies toward one side of the inner sky, while the farther end is more deeply hidden. Its exact length and angle remain uncertain because different surveys trace different stellar populations. Some studies describe a shorter, thicker central structure, while others identify a longer and thinner extension. A barred galaxy differs from a galaxy with a perfectly circular central disk. In a circular gravitational field, many stars follow nearly round orbits around the center. Within a bar, the mass distribution is elongated, so the gravitational force changes with direction. Stars respond by following stretched orbits that support the bar's shape. They do not remain fixed inside the pattern. Each star moves along its own path, while the overall concentration rotates as a large-scale structure. Several families of stellar orbits exist within the bar. Some are elongated in the same direction as the bar and form its main framework. Others are shorter, rounder, or tilted depending on their energy and position. The combined motion of many stars produces a stable pattern, even though individual paths are constantly changing. Small differences in speed and direction spread stars through the bar without erasing its overall form. The bar rotates around the galactic center with a pattern speed distinct from the orbital speed of most individual stars. Estimating this speed is difficult because the structure is observed from within and because the inner galaxy contains many overlapping components. Measurements of stellar motion, gas flow, and resonances provide estimates, but uncertainty remains. The bar may also slow gradually as it exchanges angular momentum with the disk and dark matter halo. Angular momentum describes the rotational motion of matter around a center. The bar can transfer angular momentum between different regions through gravitational interactions. Some stars move to wider orbits while others shift inward. Gas responds more strongly because clouds can collide, lose energy, and change direction. Gas entering the bar does not move along simple circles. It follows elongated streams shaped by the bar's gravity. Where different flows meet, clouds can collide or become compressed. Shock fronts may develop along parts of the bar, creating narrow lanes of dense gas and dust. In the Milky Way, radio and infrared observations reveal related structures despite the obscuring dust. As gas passes through compressed regions, it can lose orbital energy through collisions and radiation. Its angular momentum can also change under the gravitational torque of the bar. A torque is a force that alters rotational motion. The bar therefore guides some gas inward while moving other material along different paths. The process is gradual and uneven depending on cloud density, turbulence, magnetic fields, and the shape of the gravitational field. Some gas remains on elongated orbits within the bar. Some gathers near resonances, regions where orbital frequencies interact with the rotating pattern. A resonance can trap matter or change its path over time. These effects create lanes and concentrations within barred galaxies. In the Milky Way, the arrangement is difficult to separate because the observer looks through many layers of gas at once. Stars within the bar include a wide range of ages and compositions. Many are old, but younger stars are also present where gas remains available. The bar is therefore not formed in one brief event. It develops and changes across billions of years as stars are rearranged and new stars appear in selected regions. Its present structure reflects both the early formation of the inner disk and later gravitational evolution. The bar may grow from an instability within a rotating stellar disk. A disk that begins nearly circular can develop an elongated pattern when small gravitational differences reinforce one another. Computer models show that bars can form naturally in many spiral galaxies. Once established, a bar can persist for long periods, though its thickness, length, and rotation may change. Interactions with gas stars, dark matter, and satellite galaxies all contribute to its evolution. Vertical motion also affects the bar. Some stars move above and below the central plane on regular orbits, giving the inner part of the structure greater thickness. Seen from certain directions, this form can appear box-shaped or peanut-shaped. The Milky Way shows evidence of such a structure through infrared star counts and measurements of stellar distance. The thicker inner region remains connected to the longer bar lying closer to the disk plane. Dust hides much of the bar's visible appearance, but the dust itself traces the movement of gas. Warm grains emit infrared light, while dense clouds absorb radiation from stars behind them. Radio signals from molecules reveal velocities and temperatures. Together, these observations show streams of material following the elongated gravitational field. They also reveal that the bar is not perfectly symmetrical, as cloud concentrations differ between its two sides. The central bar acts as a slow organizer of the inner Milky Way. Its rotating mass changes, stellar orbits, redirects gas, creates compressed lanes, and transfers angular momentum across the disk. No single star controls its shape, and no cloud remains permanently within one stream. The structure emerges from the combined motion of billions of stars and vast amounts of interstellar matter. Across this elongated region, gravity steadily turns circular motion into ordered curves, guiding the inner galaxy through a cycle of redistribution over time. Surrounding the innermost part of the Milky Way, the galactic bulge forms a dense concentration of stars that rises above and below the thin disk. It does not resemble a simple sphere. Its structure is thick, elongated, and shaped by the central bar, with some regions appearing box-like or peanut-shaped when viewed through infrared surveys. Dust hides much of the bulge at visible wavelengths, yet longer wavelengths reveal a crowded, stellar environment where countless points of light overlap along every line of sight. The bulge extends across several thousand light-years and contains a large share of the galaxy's older stars. Its boundaries are gradual rather than sharp. Near the disk bulge, stars mix with stars from the inner disk and bar. Farther above and below the plane, the density declines, but the population remains much richer than in the outer halo. This blending makes it difficult to assign every star to a single component, especially when distance, motion, and chemical composition overlap. Many bulge stars are red giant stars that have exhausted hydrogen in their cores and expanded during a later stage of evolution. Their large size and brightness make them useful tracers through the dusty inner galaxy. Infrared telescopes count these stars and measure how their brightness changes across the sky. The resulting patterns reveal the three-dimensional form of the bulge and show that the nearer side of the structure appears brighter and more populated than the farther side. The bulge is old overall, but it is not composed of one uniform generation. Most studies indicate that a large fraction of its stars formed more than 10 billion years ago, during an early period of rapid galactic growth. Other populations may be somewhat younger, especially near the plane where gas and disk stars are more common. Determining precise ages is difficult because crowding blends light from neighboring stars and because dust changes apparent color and brightness. Chemical composition varies widely across the bulge. Some stars contain relatively high amounts of iron and other heavy elements, while others are metal-poor and resemble ancient halo populations. The metal-rich stars are often more strongly associated with the box-like structure of the bar. The metal-poor stars tend to follow rounder distributions and move with different patterns. These differences suggest that the bulge forms through more than one process over the history of the Milky Way. Heavy elements record repeated generations of stellar evolution. Early stars form from gas with little material beyond hydrogen and helium. As stars age and die, they release carbon, oxygen, iron, and many other elements. Later stars inherit this enriched material. The bulge contains stars with a broad range of these chemical signatures, showing that star formation and enrichment proceed rapidly in some periods and continue unevenly afterward. Stellar motion provides another way to separate the bulge's populations. Many stars move in orbits connected to the rotating bar. Their paths carry them above and below the plane while maintaining the thick inner structure. Other stars follow more random, less strongly rotating orbits. Measurements of radial velocity, the motion toward or away from the observer, combine with proper motion across the sky to reveal these patterns. Large surveys show that the bulge rotates, though not every population rotates at the same rate. The box-like or peanut-shaped appearance arises from the vertical motion of stars within the bar. Over time, instabilities cause some stellar orbits to rise farther from the plane. From a side view, the combined paths produce two broad lobes above and below the center. From the solar neighborhood, this structure appears through differences in the distances and brightness of red giant stars. The pattern does not represent separate clouds of stars, but one continuous arrangement of related orbits. Crowding is one of the defining conditions within the bulge. Stars lie much closer together on average than in the solar neighborhood, though they still remain separated by vast distances. In dense fields, a telescope may record many stars within a tiny patch of sky. This makes precise measurements challenging. Adaptive optics, infrared detectors, and repeated observations help separate neighboring sources and follow their motion over time. The high density also increases the chance of gravitational lensing. When one star passes almost directly in front of another, the gravity of the nearer star bends and magnifies the background light. These micro-lensing events are temporary and do not require the foreground object to emit light. Surveys monitoring millions of bulge stars detect many such brightenings. The events reveal the presence of faint stars, stellar remnants, and planets that might otherwise remain unseen. White dwarfs, neutron stars, and stellar mass black holes also occupy the bulge. They are the remnants of stars that complete their evolution. Most are difficult to detect unless they interact with a companion bend background light or emit radiation from nearby matter. Their numbers are inferred from stellar populations and evolutionary models. The dense bulge has had enough time to produce many generations of these compact remnants. Globular clusters also appear in and around the bulge. Some are rich in heavy elements and follow orbits tied to the inner galaxy. Others are more metal-poor and may preserve earlier stages of galactic assembly. Their dense stellar populations resemble small islands within the broader crowded field. Tidal forces from the inner Milky Way gradually remove some of their outer stars, while the surviving cores remain tightly bound. Dust continues to shape every view of the bulge. Dark clouds along the disk absorb visible light and create irregular windows through which more distant stars can be studied. Infrared surveys reduce this obscuration but do not remove it entirely. Astronomers must estimate how much dust lies along each direction before determining a star's true color and brightness. Small errors can alter inferred age, distance, and composition. The galactic bulge is therefore not a single ancient sphere resting at the center of the disk. It is a layered, stellar structure shaped by early star formation, chemical enrichment, the growth of the bar, and the long rearrangement of orbits. Its stars fill a thick volume above and below the plane, moving through a crowded field that changes only slowly. Across this dense inner population, the Milky Way preserves a deep record of its earliest growth and its continuing gravitational evolution through long cosmic time. Within the innermost few 100 light-years of the Milky Way lies the central molecular zone, a compact region containing an unusually large concentration of gas and dust. Although it occupies only a small fraction of the galactic disk, it holds a substantial share of the galaxy's dense molecular material. The zone appears as a broad, irregular band around the center, shaped by gravity, orbital motion, magnetic fields, radiation, and repeated injections of energy from young and aging stars. Most of the gas is molecular hydrogen, but this molecule remains difficult to observe directly at low temperatures. Astronomers trace it through carbon monoxide, ammonia, formaldehyde, and many other molecules that emit at radio and submillimeter wavelengths. These signals pass through the heavy dust that blocks visible light. They reveal giant clouds, narrow filaments, compact clumps, shells, and streams moving through a crowded environment. The gas density is far greater than in most parts of the galactic disk. Some clouds contain millions of times the mass of the Sun within regions only tens of light years across. Their average temperatures are also higher than those of typical molecular clouds near the solar neighborhood. Much of the gas remains cold by terrestrial standards, yet it is often warm enough for molecules to move more rapidly and for chemical reactions to proceed differently. Turbulence is one of the defining features of the central molecular zone. Spectral lines from its clouds are unusually broad, showing that gas moves at many different speeds within the same region. These motions arise from cloud collisions, strong shear stellar winds, supernova explosions, magnetic forces, and the changing gravitational field. Turbulence creates pressure that can resist collapse even when a cloud contains a great amount of mass. This helps explain an apparent contrast. The zone contains abundant dense gas, yet its overall star formation rate is lower than simple comparisons with ordinary molecular clouds might predict. Dense material does form stars, but much of it remains supported by turbulence, magnetic fields, or rapid orbital motion. Observations indicate that local conditions determine where collapse begins. It remains uncertain which influence dominates across the entire region. Clouds do not remain fixed in place. They follow elongated and sometimes twisted orbits shaped by the mass of the inner galaxy. Gas streams pass one another, become compressed, and change direction. Some models describe the material as moving along an open stream, while others represent it as a collection of related orbital paths. The exact geometry remains uncertain because the region is observed from within the galactic plane. One prominent chain of clouds includes dense structures often identified by their appearance in infrared images. Some are dark because their dust absorbs background radiation. Others contain bright, compact sources where young stars heat nearby material. The cloud known as the brick is especially dense and massive, yet it forms relatively few stars compared with its available gas. Its strong internal motion and magnetic structure may help delay widespread collapse. Elsewhere, active star-forming complexes contain massive young stars, ionized gas, and warm dust. The Sagittarius B region is among the most luminous molecular complexes in the Milky Way. It contains dense cores, embedded clusters, and a rich chemical mixture. Radio observations reveal many molecular species, including complex organic molecules. These compounds form through reactions in gas and on dust grains under conditions of heat, radiation, and repeated shocks. Star formation occurs unevenly across the central molecular zone. Some clouds remain quiet for long intervals, while others produce dense clusters. The resulting young stars often form in compact groups because the surrounding pressure is high. Massive stars emit intense ultraviolet radiation and strong winds. Their energy ionizes gas, heats dust, and opens cavities in nearby clouds. Several massive clusters occupy the zone. The Arches cluster contains many hot luminous stars packed into a small volume. The quintuplet cluster is older and includes massive stars in later stages of evolution. These clusters are exposed to strong tidal forces from the inner galaxy. Their outer members can gradually escape while their dense centers remain recognizable for a time. Supernova explosions add further energy. When massive stars end their lives, their expanding remnants send shock waves through the surrounding medium. These shocks compress some clouds, accelerate particles, and heat gas to very high temperatures. They can also destroy dust grains and alter molecular chemistry. Repeated explosions contribute to the turbulent and uneven structure observed across the zone. Magnetic fields are unusually strong in this region compared with much of the galactic disk. Their presence becomes visible through polarized radio emission dust alignment and long, non-thermal filaments. Some filaments extend for many light years and remain remarkably narrow. Charged particles spiral along magnetic field lines and produce radio radiation. The origin and full three-dimensional arrangement of these fields remain uncertain. The central molecular zone is also filled with energetic radiation. X-rays arise from hot plasma compact stellar remnants and the interaction of fast particles with gas. Gamma rays reveal even more energetic processes, including collisions involving cosmic rays. Infrared radiation comes from dust warmed by stars and shocks. Radio waves trace both cool molecules and high-energy electrons. Cosmic rays move through the gas and ionize molecules deep inside clouds. This changes chemical pathways and affects how well the gas couples to magnetic fields. The rate of ionization appears higher than in the solar neighborhood, though measurements vary from one cloud to another. The energetic environment, therefore, reaches even into regions shielded from ordinary starlight. Temperature also varies sharply over short distances. Cold interiors can lie beside warm cloud surfaces, while pockets of hot plasma fill spaces opened by winds and explosions. Gas cools through molecular and atomic emission, but shocks and radiation continually restore energy. This patchwork prevents the zone from settling into one stable state and keeps its chemistry, pressure, and motion distinct. Despite its intensity, the central molecular zone remains structured rather than chaotic. Gravity organizes streams, pressure confines, clouds, magnetic fields guide charged matter, and radiation continually changes the state of the gas. Dense clouds gather fragment heat and disperse while stars emerge in selected pockets. Across this compact region, the Milky Way concentrates matter and energy into a restless but ordered environment where change proceeds through slow orbits, sudden shocks, and repeated cycles of collapse and renewal. At the gravitational center of the Milky Way lies a compact radio source called Sagittarius A star. It sits within the crowded inner region of the galaxy behind thick layers of dust that block most visible light. Radio infrared and X-ray observations reveal the environment more clearly. At its center is a supermassive black hole with a mass about 4 million times that of the Sun. The black hole itself emits no light but nearby stars. Gas and magnetic fields respond to its gravity and make its presence measurable. A black hole is a region where gravity is so strong that matter and light cannot escape once they cross a boundary, called the event horizon. For Sagittarius A star, this boundary is small compared with the surrounding stellar cluster. Its diameter is only a fraction of the distance between the Sun and Mercury. Beyond it, gravity declines with distance in the same way as the gravity of any concentrated mass. Stars can therefore orbit safely at much larger distances without falling inward. The clearest evidence for the black hole comes from stars moving around an unseen central point. Infrared telescopes track these stars through the dust over many years. Some follow elongated orbits and pass very close to the center at high speed. One well-studied star completes an orbit in about 16 years. Its path shows that several million solar masses are confined within a region too small to contain an ordinary cluster of stars without rapidly collapsing or dispersing. These stellar measurements also establish the position of the galactic center with great precision. Each star follows the combined gravitational influence of the black hole and the surrounding matter. Closest to the center, the black hole dominates. Farther away, the mass of other stars and compact remnants becomes more important. By comparing many orbits, astronomers test how gravity behaves in an extreme environment and estimate how mass is distributed through the central cluster. The stars near Sagittarius A star are not all alike. Some are old, cool stars similar to those elsewhere in the bulge. Others are young, hot, and massive. The presence of young stars so close to the black hole is difficult to explain because strong tidal forces can pull ordinary gas clouds apart before they collapse. Observations indicate that some stars may form in a dense disk of gas under unusual conditions, while others may move inward after forming farther away. The relative importance of these processes remains uncertain. The central stellar cluster is among the densest known regions of the Milky Way. Stars pass one another at high speeds, though direct collisions remain rare because each star is small compared with the distances between them. Gravitational encounters gradually alter their paths. Over long periods, some stars move closer to the black hole, while others gain energy and travel outward. White dwarfs, neutron stars, and stellar mass black holes are also expected to gather in the region, although many remain difficult to detect. Gas near Sagittarius. A star follows a more changeable path. Streams of ionized gas form curved structures around the center. They glow at infrared and radio wavelengths as electrons interact with atomic nuclei. These streams do not form a stable uniform disk. They move through a complex gravitational field, collide, lose energy, and sometimes approach the black hole. Much of the gas is redirected, heated, or expelled before it reaches the event horizon. Farther inward, matter becomes extremely hot and thin. Electrons and ions move rapidly within a magnetized plasma. Friction turbulence and magnetic processes convert orbital energy into heat. The plasma emits radio waves, infrared light and X-rays, but Sagittarius A remains faint compared with the active centers of many other galaxies. Only a small fraction of the available gas appears to cross the event horizon. The low brightness suggests that the inflowing material radiates inefficiently and that much of it escapes in winds. Gas may begin moving inward from nearby stellar winds, then lose only part of its angular momentum. Magnetic fields can stir the flow and launch matter outward. The detailed structure changes over time and cannot be represented as a simple, steady disk. Sagittarius. A star produces occasional flares. During a flare, infrared and X-ray emission rises for minutes or hours before fading. These events probably occur when magnetic fields reconnect or when small concentrations of hot plasma accelerate near the black hole. The exact mechanism remains under study. The flares do not indicate that the black hole itself changes. They arise from matter just outside the event horizon. Very long baseline radio observations combine telescopes across Earth to achieve the resolution of a planet-sized instrument. These measurements reveal a ring-like pattern of radiation around the dark central region. The light comes from hot plasma bent and magnified by strong gravity. The darker interior is associated with the black hole's shadow, an apparent region larger than the event horizon because light paths curve around the compact mass. The observed size of this shadow agrees with predictions for a black hole of the measured mass and distance. Its exact brightness pattern changes because the surrounding plasma moves rapidly. The image is therefore reconstructed from observations gathered over time rather than captured as a simple photograph. It provides an independent confirmation of the compact central object already established through stellar orbits. Sagittarius. A star may have been more active in the past. X-ray reflections from nearby molecular clouds indicate that the clouds now return echoes of much stronger radiation emitted several hundred years earlier. Larger structures above and below the galactic plane also suggest episodes of energetic activity over much longer periods. The exact connection between these events and the central black hole remains uncertain since intense star formation can also release large amounts of energy. At present, the center is comparatively quiet. Stars continue their rapid orbits, hot gas circulates through magnetic fields and small amounts of matter move inward. The black hole adds mass slowly, while its gravity organizes the innermost environment. At the deepest point of the Milky Way, the luminous disk central bar, bulge molecular clouds and stellar cluster all converge around an object defined mainly by the motion of everything nearby. Sagittarius. A star remains dark at its core, surrounded by measured light and steady orbital motion. Across the Milky Way, every region remains connected by gravity motion and the slow exchange of matter. The outer darkness holds faint companions and ancient streams. The halo carries unseen mass and thin gas. The disk bends flares and gathers into spiral patterns where clouds cool and stars appear. Farther inward, crowded arms molecular clouds, the central bar and the bulge form denser layers around the galactic center. Nothing within this structure is completely still. Stars follow long orbits. Gas rises, falls, cools, heats, and changes form. Dust drifts between stellar generations. Heavy elements leave aging stars and enter new clouds. Clusters form, loosen, and disperse. Small galaxies approach, stretch, and add their stars to the larger system. These changes unfold over millions and billions of years, too slowly for a single lifetime to witness, yet clearly enough for careful observation to measure. At the center, Sagittarius A star remains quiet compared with the brilliant cores of many galaxies. Nearby stars continue around its concentrated gravity, while hot plasma gives off faint radiation before much of it moves away or disappears beyond the event horizon. Around that small central region extends the entire Milky Way, from dense molecular gas to the thin outer halo. The galaxy continues through space as one changing structure, neither fixed nor complete. Its oldest stars preserve early conditions, while young stars begin inside cold clouds. Light crosses the disk, passes through dust, and travels outward into intergalactic darkness. Across its immense scale, the same physical laws remain present, shaping every orbit and every quiet transformation through time. The Milky Way turns slowly, carrying every star, cloud, planet, and unseen particle through a calm and continuous motion.